Okay, today is Wednesday. It's 2 minutes after 11, and there are a total of 5 people here. So if we ever get these videos online, then we'll see if there's a problem. Let me just mention that, and I'll go through it if and when there are more people here. I have your exams back for you. I graded the exams on a basis of 120 points because it's easier to make each question 40 points than 33 and 30. And as you can notice, the grades were not very good. And I'm sure that these people correlate with the people who come late to class and don't do their homework. So, frankly, I've rarely seen a class that has such poor attendance and poor homework. And it's showing in the grades. There's usually a good correlation between doing homework and grades on the exams. And this is basically showing a lack of effort. People don't come to class a half hour late and they don't do the homework. It's saying, I don't really care if I learn this material or not. Of course, the people who are here now at least come on time. So we'll be talking to people who are not here. Although, as far as homeworks goes, I can be talking to everybody. Okay, so anyway, these grades don't make me happy. I'll talk a little bit more about the exam if and when they show up, so that they might actually hear it. Okay, so what have we been doing? The title of this class is Process Control, and also that's part of the title of the textbook, Process Control. You may have noticed that we haven't done any control yet. The semester is about half over. I think this is lecture 15 out of 28. And what we've done so far is we haven't done control. We've looked at systems, and we've looked at how do you model systems and how do you analyze those models. And that's a prerequisite for doing control. Before you do control and see how control affects the behavior of a system, you need to know how the system behaves even without control. So it's sort of a prerequisite. So we spend half the semester taking different systems, and if they were linear, writing linear models. If they were nonlinear, writing exact models, and then linearizing them. And then looking at how we analyze them, and in particular, looking at the different types of questions that we ask in this class from what you do in all your other classes. As I mentioned a number of times this semester, in all your other classes, you're living in the fantasy world of steady state land. Now, it doesn't mean you never get steady state, but until you get to steady state, if you ever get there, the system is unsteady. Once you're there, you can use the material from your other classes. The point of this class is to understand, will you get to steady state? Once you're at steady state, will you stay there once there are perturbations to the system? Or there could be random perturbations, but there could also be perturbations from, if you have a reactor, there could be perturbations from other parts of the plant, where the input changes, the concentration of the input changes, or a flow rate changes. So there are all sorts of things that can change. And what happens to your system? Does it remain in steady state? Is there a reason that you come late when you were just sitting in Steinman Hall 40 minutes ago?
No, I was sick. I'm sick, so I have to.
Okay. I hope you feel better, but if you're physically at City College, you should be in the classroom on time, if you're physically here. No discussion. Okay, so what we did is we looked at how we do our modeling of systems and analysis, and when it comes to the analysis, we looked at the questions we asked for about unsteady systems. And we needed some tools to answer those questions. So the first set of tools, which was the subject on the first exam, was we wrote unsteady models, something that you never analyzed in previous classes in chemical engineering. And then we used the methods of working differential equations to solve them. We then turned to methods of Laplace transform, which could do the same thing with less algebra, but we also saw there were many other advantages to Laplace transforms, because we could get a lot of information from the algebraic equations that we get once we've Laplace transformed the integral and differential equations. and solved the algebraic equations much simpler, we could get a lot of the information that we need for control without even inverting those Laplace transforms. And so, for example, we can answer questions about stability if, say, our output variable f in the Laplace domain f tilde is a numerator or a denominator, just by looking at the roots of the denominator. And that can tell us about the stability. Will the system, in response to some perturbation, decay back to a steady state? Will it decay with an oscillation? Will it just oscillate forever without decay? Or will it go off very far away to infinity? What does infinity mean? Generally, it won't come back to this. What exponential increase means it will, instead of going back to the steady state, it will increase to a point where the linear model no longer holds, and the nonlinear model will control what happens. But in particular, it won't go back to the steady state. Moreover, we can understand a lot of the response to oscillatory inputs, also directly from the Laplace transform. We understand that if the model is linear, the output frequency will also oscillate if the input oscillates, and they'll oscillate at the same frequency if we have a linear model. Moreover, we can get the amplitude ratio between the output oscillation and the input oscillation, as well as the phase lag, all without inverting the Laplace transform. And that's sort of really nice because the Laplace transform is much easier to deal with than the actual variables themselves. What we will be doing in the next class is, just as we start control, we're also going to spend one class looking at a program written by the same company that puts out MATLAB. It's actually part of MATLAB, called Simulink. And what Simulink allows you to do is it allows you to actually solve these equations numerically and to use the notion that we've come up with, and we will be using much more of block diagrams. And we basically put our block diagram onto the computer, and it can give us the output. And we can look at what happens as we vary different numbers. Now, we looked at various examples and various types of problems. And in chapter 5, what we did is we tried to organize them in a way that makes, that's sort of the most, put them into categories. We started out by looking at first order systems. And then we looked at second order systems. And then we looked at systems in series. And we looked at systems in series, which we call non-interacting, where if we have a system, the J system in a series, the J system only depends on the J minus first system and not on the J plus first system. So that you could solve system 1 without worrying about system 2. Once you have solved system 1, you can solve system 2 based on what you got from system 1. And then you could solve system 3 based on system 2, etc. You could solve the systems one at a time. That's called non-interacting. And what we saw in non-interacting systems in series, that the overall G tilde transfer function was just the product of the transfer functions of the individual processes. Very, very simple. And the roots of the denominator of the entire system in series was just all the roots of the individual systems. So if the individual systems were stable, so was the whole chain of systems. As opposed to that, we looked at the interacting systems, where to solve, say, system 3, I need to know the answer to system 4 and system 2. So I can't solve them in sequence, I have to solve them all together, because each one is dependent on the next one and the previous one. So if I were doing that without Laplace transforms, I would have to solve all those equations at the same time. Whereas if I'm looking at a non-interacting system, I could solve the equations for the first system without worrying about anything else, and then go to the second system and just solve that one at a time. And the second system just knowing the answer to the first system. With an interacting system, I can't do that. I can't solve things sequentially. I have to solve everything at once. So obviously that's more complicated. And what we found at the end of the last hour was that in contrast to the non-interacting systems, the interacting system, the stability, the roots of D tilde of the interacting system were related to the roots of the individual systems, but they were different. And what we saw was that, whereas in the non-interacting system, the roots of the denominator that determine the stability of the overall system is just the set of the roots of the denominators of each of the individual systems. In the interacting system, what we found is they're the same number of roots, but they're more spread apart. So for example, what we found is that there was one root, generally going to be one root in the interacting system that's much smaller than any of the roots in the non-interacting system. Now what does smaller mean? If you remember, it's those roots of the denominator that if we were to do the Laplace transform inverse, would come as the exponents e to the alpha t. So if alpha is much smaller in the interacting system, then instead of the exponential going down quickly, it could take a long time to go down. Meaning, if there's a perturbation to the system in an interacting system, even if the system goes back to steady state, it could take a lot longer than if I have a non-interacting system. That's life. It's not like we can now make it non-interactive. We just should be aware of that. And even if something is stable, but it takes a long time to go back to steady state, we have to worry about that in our control system. If say the desired specs, the set point, is 95% purity on a product, and we have a perturbation that's giving me 85% purity, well, if it goes back to steady state in 5 minutes, we can probably live with that. If it takes a week, we can't live with that, because all that material is just going down the drain. So obviously that's something that we need to be cognizant of. Okay, well, before I go on to some new material, I'm going to talk a little bit about the exam. How many are we here? 2, 4, 6, 8, 10. Okay, we have half the class here. Obviously the other half of the class doesn't believe in waking up early enough to get here by train, when every week there's at least one of the 2 days there's a delay on the train. It basically shows they don't really care about this class. Okay, so I'll give back the exams at the end of the hour, so I don't want to distract from the hour. But as I said, the exam was graded on the basis of 120 points. The grades were way down here. Basically, anything around here is sort of garbage points. When I say garbage points, that means if you basically copy the question and just write the general equation, you get a few points. Doesn't really show that you know what you're doing. I usually weight the points a little bit more towards the beginning of the problem than towards the end of the problem. So we've got a problem that more than half the class doesn't seem to know how to start any of the problems, which is very worrying. What's even more worrying is calculus. Calculus is a prerequisite for all the courses in the curriculum. I would say very few people in this class know calculus. So for example, when in problem 1, when I ask people to come up with a Taylor series, all that requires is taking derivatives. You know how many people wrote the following equation? You know how many people thought that, no, actually they had even worse. It was this one. E to the d dx and e to the x. They wrote it x e to the x. You know how many people wrote that? That the derivative of e to the x was x e to the x? It was more than one person. If anyone is writing this, I don't understand that. Coming up with the Taylor series was literally taking derivatives. You know how many people did not know how to take, how many people thought that a dda of a to the m was equal to dda of a to the m plus 1? You know how many people wrote that? More than one. When people are writing things like this, that's telling me that they don't know calculus, that they can't take derivatives. And if you can't take derivatives, nothing else follows if you don't know calculus. Calculus was a prerequisite for 228. We're way beyond 228. This is not satisfactory when people don't know how to take derivatives. I don't even want that on the blackboard, because someone may come in here and think I'm teaching nonsense. The problem with that had the most cognizance was the second problem. But there were problems with that one as well. And the third problem was also a disaster. The third problem, which is a problem with the room heater. We had a heater, we had that little house. Some people drew very nice pictures of houses, but didn't know how to do the algebra. But we had a house where we had a heater that had that instead of being on and off, but its level of being on was proportional to the difference between the set point and the temperature in the house. So it was a sort of a continuous heater. So QH was K times theta set point minus theta in the house. Theta is the temperature. There were people who wrote down equations, rho V CV dt dt was equal to something plus K theta set minus theta, and didn't realize that theta was the temperature. They didn't realize that this T was the same as this theta. There were other people who decided, I don't like the problem you're answering, so I'm going to answer a different question. You know how many people did that? Half the class. Half the class decided they didn't like the fact that QH was a function of theta. So they just assumed it was a constant and copied the problem that I did in class onto the exam. Now, if you don't like the problem I'm asking, you can't do a different problem. You can ask me, which is why I'm sitting here, you can ask me, what do you mean? And I'm happy to tell you during the exam. But if you decide you're going to copy a problem out of the book rather than the problem that I'm asking, you're not learning the material, you're not thinking. Clearly, this should have been a theta. And of course, we also had losses. We had in minus out. Well, here we just had a UA theta out minus theta. So anyone who paid attention at all would say, gee, there's a theta here, and a theta here. Why don't I bring these two terms to the other side of the equation? The number of people who did that was about 5 out of 19, out of 18. 5 out of 18. If there's anything I've been stressing all semester when you do these problems, is you bring all the terms of the theta to the left side of the equation. Somehow, most of the class, no matter how many times I did that on the blackboard, decided, no, I'm going to assume this is a constant because that's the problem that was done in the book, and ignore the fact that it's a function of theta. Again, if you don't like the problem I'm asking, you can't just copy a problem in the book. Another thing, in problem 2. In problem 2, I had a rate equation, which was KCA over 1 plus K times CA squared. Just check to make sure that that's the one I asked. Yeah. Minus. And of course, this is done linear because I've got stuff in the denominator. It's not just CA. Obviously, what you need to do is linearize this term. Some people have thought, well, gee, I don't like taking derivatives of quotients because I learned that as a freshman and I forgot that. So I'm going to take the derivative of CA squared. So people then just decided to write that CA squared was equal to CA 0 squared plus 2CA 0 times CA prime. That's true, but it's irrelevant for this problem. This is not CA squared. So obviously, when you write this linearized, you have to write this as K times CA over 1 plus K prime CA squared at the reference state, whatever reference state you're linearizing about, plus the derivative plus CA prime times the derivative, ddCA of KCA over 1 plus K prime CA squared. Now, this is taking the derivative of a quotient. I think 3 people figured out how to take the derivative of a quotient. Again, this is material from your first semester of calculus. We're not even talking about the second semester of calculus, the first semester of calculus. If you're having trouble taking the derivative of a quotient, what you need to do is spend a weekend doing nothing else but reviewing calculus. You've all learned calculus. You've all passed calculus, otherwise you wouldn't be here. So you all knew this at one point. But somehow, people haven't figured, most of the class hasn't yet figured out that you need to review your earlier math classes to be able to understand what's going on in this class. Like, that's not a hard concept. This class requires some facility with basic mathematics. So if you've forgotten, which is natural, if you haven't used something, you forget it. But it's like, take it from me, it's like riding a bicycle. You go back and you look at it and you practice it, and it comes back to you. So what I would really do not want to see again on future exams is people not knowing how to take a derivative. That's not acceptable. You all know how to take derivatives. At least you knew, so you need to review your calculus so that you don't make these mistakes again. Now I have obviously I wrote out the complete solutions of these with point values for each. Anyone who's interested in seeing the solutions is welcome to come to my office and look at them. You can't photograph them, but you can take notes. If you want to read through them and take notes, that involves thinking. That I'm happy if you want to think. If you want to photograph, that's not thinking. So there are no more photographs, no photographs of that. But you're welcome to sit in my office when I'm there and look at the solutions and think about them and take notes on them. But I'm not handing them out because that is useless. People then, they don't think when it gets handed out. If you want to come to the office and think, please, you're more than welcome. Again, I also always have office hours every week, although tomorrow I have to leave early because I'm going recruiting at another school. But generally, I have office hours every Thursday. And if people can't make the office hour, they're always welcome to schedule another time with me, and I'll schedule another time. So I'm flexible as far as that goes. Okay, are there any questions on this? So there were 3 questions. One that required was on probability, that required just a little bit of basic calculus. Essentially, no one got very far on that. A few people got the Taylor series, but amazingly, nobody got very far on that. I don't quite understand why, because it didn't really require much deep knowledge. It just required a little calculus. All it required, it was basically just calculus, that problem. Problem 2, a small number of people knew how to take a derivative of this. The minority of the class knew how to take a derivative of that. Again, there's no excuse for that. You learned it, you just need to review it. You need to know how to take derivatives. Full stop. And in the third problem, people refuse to think. You're given this. You see a theta there. Don't just copy a problem out of the textbook or out of the notes. I mean, that's the downside when I make a problem, exam open book. People decide, instead of thinking, I'm going to look at the book for a problem that looks somewhat similar and just copy it. Well, it's similar, but it's not the same problem. You can be certain, I will not ask you a question where the answer is in the textbook. I will not ask you a question where the answer is in the notes. When any question I ask you requires you to think. I know that sometimes it's scary, but I want you to think, because when you go out and graduate and you go out and get a job, I assume you want to do well in your job and get a promotion. I assume you don't want to get fired. Maybe it's a bad assumption, but I assume you want to do well. If you want to do well in a job, you have to think. Every job wants you to think. They don't want you to copy things out of textbooks. And trust yourself, it's not that hard. You're all capable of thinking. Just don't be scared to think. You've got nothing to lose by thinking. Okay, now I've preached for almost a half hour. It's time to get back to the material. Any questions? On the next exam, I don't want to see this. I only want to see this on the next exam. And you made it to be seniors. Everyone is capable of getting half the points on any exam I give. Each of you is capable if you try. I don't expect people to get up 120, but 50 or 60 on an exam is okay. It's a decent grade. I'm sorry, when is the next exam? Pretty soon. It's going to be pretty much the material through the end of this class, maybe a little of the next class. I don't have the book in front of me, but it's going to be before we start control. We're starting control probably in the next class, within the next class or so. So it'll be everything through the end of chapter 5. I don't recall what's chapter 6. So again, everyone in this class should be capable of getting at least 50 points out of 120. If anyone who is down here hasn't reviewed calculus and/or has refused to try to think. They get so scared, they said, let me copy something out of the textbook instead of thinking.
I'm just curious, were each sub-questions worth the same for the...
No, it depends. Some questions were long, some questions were longer, some are shorter. As I said, you're welcome to come to my office and look at the solutions with the point values for the different parts of the question. Generally, the beginning parts of the question are worth more than the latter parts. Generally. Now, that doesn't mean that the latter part, if the latter part has 10 parts of the last part, then that's certainly worth something. But generally, I want to see that people can get the problem started. And if they do all the details on of the algebra later on, that's something else. But write down the problem, move this to the other side of the equation, take the Laplace transform, etc. That I want to see people do. Linearize the problem properly. I want to see people do that. Other questions? Okay, so I'm going to erase this. There's no need to have that on the blackboard. All right, one thing you might recall is when we were looking at n non-interacting systems in series, n first order non-interacting systems in series, If we were looking at the output, y prime of t versus t over t. And what we saw was when n was 1, it looked like this. When n was infinity, we used a different color chalk. This was n goes to infinity, which looked like the plug flow reactor. This was n equal 1. And in between we had so this was the n equal 1. And this was the direction as n went up. So what's the point here? Why am I writing this again? I'm writing it again because what we found was that when I have n first order systems in series, as n gets large, the system starts looking like a plug flow reactor. And here we were looking at a plug flow reactor with no reaction. So if you remember in a plug flow reactor, if there's no reaction, then what comes in comes out. But it doesn't come out right away. It comes out tau seconds later. So if I have in looking like this versus t, then out looks the same, but this difference is tau seconds, or minutes. So it's just a delay. So the plug flow with no reaction is just a delay. And what we see here is that the first order systems, at least if I have a lot of them, they kind of look like a delay. That there's some relationship between first order systems and delays. Now, of course, a single CSTR is not a delay. A single CSTR in a single CSTR, if there's a change in the input, it's immediately felt in the output, but it's felt slowly because it's diluted in what's in there. So in a single CSTR, if this is the input, then the output, there's an effect immediately, unlike here, but it's gradual. Well, it's exponential, but it's not a step change. There's a step change here, and then there's a step change in the input, but there's only a change in the derivative of the output. But obviously if I have many of these in series, then if there's a step change here, well, there's a change in the first derivative here, and the second derivative, blah, 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 blah. And eventually, when I'm in series, in first order non-interacting systems in series, with a bunch of delays. So the first order systems in series, we know we get a product of KPIs over the product of 1 plus STI. And for each of the delays, we have an e to the minus s theta. So I have to multiply them together. And when I multiply exponentials, I just add the exponents. And we call this J. So these are the delays, and these are the first order systems. Now, because of this somewhat relationship, or somewhat a relationship, you can notice that e to the x is equal to 1 plus x squared over 2 factorial plus dot dot dot. You know, this is the Taylor series I asked you to come up with on the exam, which almost nobody could do. If I linearize this, and I chop it off here, then I also notice that, so this is e to the minus. So obviously e to the minus x is 1 over e to the x. And I can approximate that as 1 over 1 plus x.
Even negative s and the sum of theta I, theta represents temperature or?
No, these are delays. Theta represents the delay of things at theta j seconds in this particular case. So these are delays. Delays, theta 1, theta 2. Okay, so what that says is g tilde of s can be approximated by product of KPIs over the product, let's make this k, so I don't keep myself, 1 plus s to k. And e to the minus s times the sum, I can move the e to the minus x to the denominator and make it e to the plus s. And each one of them I can write as 1 plus x. So I can write this as the product on j of 1 plus s theta j. Because each one of them, so the product of them, looks like this. So another way of noting that is I can just write this as the product on j of e to the minus s theta j. So each one of these I bring to the denominator, and I write this. Okay, so each one of them I write as 1 plus x. That's probably a nice way to write it. Now, let's just look at the denominator. Let's multiply these things out. If I have a bunch of terms 1 plus something, I'm multiple terms that are 1 plus something. So this is going to be 1 plus. Now, if I look at s, I'm going to get a polynomial here. So if this goes to n, and this goes to n, eventually I'm going to get a polynomial with an s squared plus dot 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 plus s to the n plus n times something. So I'm going to get a polynomial here. The leading order, the first term in the polynomial, is I'm going to have each one of these terms stk or s theta j multiplying a whole bunch of ones. Because otherwise, that way I only get one s. If I have any of these multiplying each other, that'll come into the s squared or the other terms. So what I'm going to get here is the sum on k of the tk plus the sum on j, 1 to n, theta j. So you can notice that the coefficient of the s to the first power is a sum of the time constants for the first order systems plus a sum of the delays. And now, if you remember, when I'm looking at long times, the final value theorem. In the final value theorem, I'm looking at the limit as s goes to 0. So from the final value theorem, we know that t goes to infinity somehow corresponds to s goes to 0. Of course, I can be more specific. It's the limit as t goes to infinity as s goes to 0 of s n kilometers. That's more specifically what it says. But it basically says t goes to infinity refers to s goes to 0. When s goes to 0, all these other terms of higher power mass are small compared with the linear term. So that says if I'm interested in the long time and what's going on at long times, it looks like G tilde looks like the product of the KIs, APIs, divided by 1 plus s times the sum of the TKs plus the sum of the theta j's. In other words, the leading order looks like a first order system with a very long time constant. So there's something nice going on here is that the effective time constant is quite long. So the effective steady state gain is this. But the effective time constant is what I just wrote there. Even though the total delay that's the total delay. Are there any questions on that? Now, what's the significance of that? What the significance of that is remember, when we have perturbation, then we have solutions that are going to have exponentials in it in time. And there's going to be a time constant for each one. And when I have these delays, then what this is telling me is that part of the slow part of the response of the system is going to be on this effective time scale. So it can take a very, very long time to get back to where it started. And that's how one of the things that delays can do here is that delays can cause a long time lag between the effect of a change, between when the change happens and its effect. So that can come in when we do control is that if we control based on what we measure now, then, and we do an action, we can't a second later adjust our control based on what we see a second later. We have to wait for the effect of what we just did to kick in. And we'll see that as we go along. Now, we've only looked at systems in series. Notice I wrote the word series. These were series. What happens in parallel? So let's look at that particular case. And I can look at it here. And here I have x coming in. And I'll have that as a G1 tilde and a G2 tilde. And it's going to come out as a Y prime tilde. Y prime. Okay, so let's notice from our block diagrams, what can we say about, so here I have x1 prime tilde, x2 prime tilde, y1 prime tilde, y2 prime tilde. Make sure before you leave that you sign this, because I'm keeping track of Mrs. Class, and as I said, once people miss 4 classes, then they get the opportunity to take this class next year. Because I'm going to drop them from the class, take the system in this class. And that includes subway delays, because subway delays happen every day. So you have to leave your house early enough. Okay, so what do we know about x1 prime, x2 prime, and x? What's the relationship between them? They're all equal. And what do we know about y1 prime, y2 prime, and y prime? Somebody else?
y1 and y2 sum to y prime?
Yeah. So I have y prime is equal to y1 prime tilde plus y2 prime tilde. And how do I relate y1 prime tilde to x1 prime? Somebody else? Multiplied by g. So this is equal to G1 tilde times, we said these are equal, times x prime tilde. And what about, we have to add to that something. What is y2 prime tilde in terms of x2 prime tilde? And x2 is just x, so I have g2. Okay, so let's look through this. Let's assume that that G1 and G2 are both first order systems. So we can call this whole thing G tilde. So G tilde, if these are first order, then we know that this is KP1 over 1 plus ST1 plus KP2 over 1 plus ST2. So let's see what that is. Let's bring it all into one. Let's do the algebra to bring it into one denominator. So I've got 1 plus ST1, 1 plus ST2, times KP1, 1 plus ST2, plus KP2, 1 plus ST1. And let's sort that out a little bit. Let's take KP1 T2 plus KP2 T1 divided by T1 plus T2. Or by KP1 plus KP. Let's divide it by KP1 plus KP. So let's let that be KP. And notice this KP is, so I have KP1 over KP1 plus KP2 times T2, plus KP2 over KP1 plus KP2 times T1. KP1 over KP1 plus KP2 is a fraction, less than 1. KP2 over KP1 plus KP2 is a fraction less than 1. And the sum of those two fractions is 1. So it says I take, say, a third of this and 2/3 of that. Something like that. So obviously I'm going to get something between T1 and T2. So this is between and T1 and T2. But before I go through, let me just make sure I've done that correctly. So all right, so let's rewrite this and see if that's actually what I want. So I've got a KP1 plus KP2, and then plus S times KP1 T2 plus KP2 T1, divided by 1 plus S T1, 1 plus S T2. So what I'm doing here is I would like to divide by multiply, factor out KP1 plus KP2. So I've got KP1 plus KP2. Factor that out. Comes 1 plus S, KP1 T1 plus KP2 T2 over KP1 plus KP2. Divided by 1 plus S T1, 1 plus S T2. So notice if I don't want to call this KP, I want to call this T3, because it's a T. The units of the KPs have canceled out. This is units of time. So this is some T3, and T3 is between T1 and T2, for the reason I mentioned here. And I could let KP overall equal to KP1 plus KP2. So that tells me that G tilde of S from here is just KP over 1 plus ST1, 1 plus ST2. And this is now just 1 plus ST3. So when I series two product first order processes in parallel, as opposed to in series where they just multiply by each other, when they just multiply each other, product to product. Here, when they're in parallel, yeah, the denominators are multiplied, but I also have the numerator. And so that's interesting. And I've also created a new term constant, T3, where that term constant is between T1 and T2. By the way, this type of analysis of saying a third of something plus 2/3 of something else also came up on the exam, but no one got it. That was also part of one of the problems. Okay, so what does this mean? Well, the first thing it says is I can invert it. Now, yeah, so if I want to invert this, we go to our table. So what line in the table should I be looking at? Someone has an answer there? And let's do it for step changing. Step changing. So y prime delta of s is 1 of delta x over s times g tilde of s. So I have 1 over x times this. What line of the table will give me that? 9, yeah. So if I do the inversion, I find that y times t and y9. So the constants come along from the right. I've got kp delta x. And no, it's line 10. Line 10. Because I have the 1 over x. And that's multiplied by 1 minus, and I need to identify a is this coefficient is t3. So I've got 1 minus, t1 minus t3 over t2 minus t1, e to the minus t over t1, minus, I'm sorry, the first one is plus, the second one is minus t2 minus t3 over t2 minus t1, e to the minus t over t2. Okay, now remember T3 we said is between T1 and T2. So one of these is going to be plus and one of them is going to be minus. because T3 is bigger than one of them. So let's say that T2 is bigger than T1. If T2 is bigger than T1, then the denominator is plus. But T3 is bigger than T1, so this is minus. But this is plus and this is plus. So they would both be minus, for example. Okay, now what does this look like? Unlike the simple case, remember when I only had a single term on the right, for example, when we were evaluating using line 5, we would get 1 minus little t over dt, and it looked like an upside down exponential. Here I've got two of them fighting each other. Two exponentials fighting each other, and they each have different sign constants. So what does it look like? Well, let's plot what it could look like. And this is say y prime versus. Well, it can certainly look like this. That's sort of what we would like to see. It doesn't have to be quite as look something like this. But it can also look like this. So this depends on the values of the t's, on T1, T2, and T3. And notice that sometimes this could be monotonic, like the ones in the middle, but sometimes it can overshoot. And sometimes it can dip. Call this inverse behavior. What does that mean? I start out here, and there's some perturbation in x. And if I look at the Kp, so this difference is Kp for y prime. So it started out y prime was 0 here, and then we had a steady state gain is the value of Kp, where Kp is this is Kp1 plus Kp2. But who said that each of these has to be positive? Some Kp's can be positive and some can be negative. So what happens? What we have here is now each Kp, Kp1, belong to T1. Kp2 belong to T2. So T1 and T2 are time constants. The overshoot could happen is if the fast time constant, the one with the smaller T1, is positive, the fast T has Kp greater than 0. So initially that happens, but then once the fast T decays after a while, it's irrelevant, and then later on the slow T has Kp less than 0. So it responds to the fast time scale, and then it has to relax back down because the Kp for the other one is negative. Similarly, the inverse behavior, you could have the fast T corresponding to the Kp negative, followed by the slow T corresponding to Kp positive. So first, it only sees the fast T, so it goes down. But then the slow T comes in and it starts going up again. So what you can see is once you have systems in parallel, once you have stuff in the numerator, you can get stuff that's more interesting behavior. Interesting sometimes means hard, but hard isn't necessarily bad. It's interesting. Okay, any questions on that? All right, well, let's look at another situation where we have a recycle. And remember when we did, let's look at a recycle situation. In a recycle situation, if you remember when we were doing block diagrams, we found we had one problem with a recycle where the denominator looked funny. It looked like a 1 minus a bunch of g's. So let's just look at an example here. So let's say I have a CS field, or some sort of reactor. And what comes out, so I have an input. And what comes out, so let's say I have an exothermic reactor. Exothermic reactor. So what comes out is hotter than what went in, because I have some reaction. So this stream comes out, and I use it to heat up the feed. So let's say this is theta 0. This is theta 4. And I want to get the numbers consistent with my, with what I've written here. And let's call that theta 3. So what I'd like to do is I'd like to analyze the system. Notice that there's a feedback because the heat from the reactor is then used to heat up the feed. So let's focus for a minute. First, focus on heat exchangers. And I'm going to assume that the heat exchanger has a much faster time scale than the reactor. So it relaxes to steady state much quicker. So let's see, I also need a number for that theta. What am I going to call that theta? Actually doesn't matter. Okay, so what I'm interested in is theta 3. I'm interested in theta 3. So if I look at rho v CV, d theta 3 dt, where this is the volume of the heat exchanger, and rho and CV depend on our fluid properties, and that's equal to the flow in, which is rho v CP theta 0 in minus out, theta 3, in minus out. And then so this is what's coming in, what's coming out, and then I have the heat exchanger part. So then I have plus UA times the heat exchanger part. And we said we have we earlier in the semester, a couple of weeks ago, we came up with a kind of a dumb linearized version of how a heat exchanger works. We know we should have delta T log mean, but instead we have theta 4 minus 1/2 theta 0 plus theta 3. Remember that? Okay. So now if we assume that the heat exchanger time scale is much faster than the reactor, then we need a bigger piece of chalk. Then, if you remember, if the time scale is much faster, we can assume that it is always in steady state. And the steady state consistent with theta 4 coming out of the reactor. That's a lot of verbiage. So in that case, I can neglect the left side, and I can rewrite this as 0 is equal to theta 0 minus theta 3 plus UA over rho VCP. Times, and let's factor out the 2. And I've got 2 theta 4 minus theta 0 minus theta 3. So I just set this equal to 0, and first I divide it, and I divide it by rho v CP. And I factor out the 2. And now what I want to do is solve for theta 3. So let's bring the theta 3 to the other side of the equation. I've got theta 3 times 1. And I want to call this thing alpha, so I don't have to carry it around. So I've got this here, 1 plus alpha. And that's equal to theta 0 times 1, that's this guy, And then I have minus alpha. And then I have a theta 4 times 2 alpha. Is that clear? Just algebra. So now I have theta 3 is equal to 1 minus alpha over 1 plus alpha times theta 0 plus 2 alpha over 1 plus alpha times theta 4. So I want you to notice that theta 3 is the sum of two things. And they're not just plain thetas, they're thetas times something. So let me call this thing theta 1 and this thing theta 2. Just giving it a name. And I'm going to call this thing G1 and this thing G2. And this suggests that I can write the heat exchanger as a block diagram. Because I have, let's write the heat exchanger as a block diagram. So I've got theta 3 coming out. Theta 3. But theta 3 is the sum of two streams. So it's the sum of this stream and this stream. And this one is theta 1. And this one is theta 2. Because this tells me it's a sum. And theta 1 is a G times theta 0. And theta 2 is a G times theta 4. So right now, this is the block diagram for the heat exchanger because it exactly reflects this equation. And now let's do the rest of this. I have a reactor which takes theta 3 and turns me into theta 4. So I've got a reactor, which is G for the reactor, and that takes me into theta 4. So this is the block diagram for this system. And if I have a block diagram, the nice thing about block diagrams is if I know the individual G's, I can come up with the G for the whole system by putting together the pieces instead of doing it all at once. So why don't we go through? Let's look at theta 4. Theta 4, how do I relate theta 4 to theta 3? Someone who hasn't answered yet. Who hasn't answered yet? No, you haven't answered yet. How do I relate theta 4 to theta 3? How do we relate theta 4 to theta 3?
Theta 3 plus theta 2.
I can't hear you.
Theta 3 plus theta 2.
Look at the picture. Theta 4 to theta 3. How do I write theta 4 to theta 3? That's an answer. You have an answer.
It's a theta 3 times GR.
Right. So it's GR times theta 3. This is block diagrams. If you're having trouble with this, you haven't looked at your previous notes at previous classes. That has to change. Remember? People who don't do their homework, don't come to class, don't look at their notes. Do you want to be here or do you want to be here? You have to decide where you want to be. And I will oblige, because I have to give you the grade based on your tests. But the mechanism of getting here from here is looking at your notes before you come to class and doing the homework and asking questions. That's the mechanism of how you do it. Okay, so now we know what is G. What is theta 3 in terms of theta 1 and theta 2? Plus theta 2. Theta 1 plus theta 2. But what is theta 1 and what is theta 2? Well, actually, for theta 3, I can just plug this in. I have it right here, so I don't have to belabor it. GR tilde, this is E times, From here, this is just G1 tilde theta 0 plus G2 tilde theta 4. Now I can see that from here because it's equal to theta 1 plus theta 2. Theta 1 is G1 theta 0, and theta 2 is G2 theta 4. But now I want to solve for theta 4 because it's on both sides of the equation. So I have theta 4 times 1 minus GR tilde G2 tilde. I just move this to the other side of the equation. Is equal to GR tilde G1 tilde theta 0. Or theta 4, and these probably should be tilde all. Should really all have tildes on. Is equal to GR tilde G1 tilde over 1 minus GR tilde G2 tilde times theta 0 tilde. So notice when I have recycle, I get these funny denominators. I get these denominators that have a 1 minus something in it. Notice if I had no recycle, if I had no recycle, that would tell me that, let's see, alpha. So if I had no recycle, then G2 would be 0, because I wouldn't be recycling it. G2 would be 0. So that would correspond to alpha is equal to 0. No recycle corresponds to alpha equal to 0. Yeah, so there's no heat transfer. Alpha is equal to 0. Which corresponds to G2 0. So in that case, theta 4 tilde, if G2 is 0, will just be equal to GR tilde times theta 0 times G1 tilde. But G1 tilde, if alpha is 0, is just 1. So if I have no recycle, then the stability of the system is governed by the denominator of GR tilde. If I have recycle, it's not the denominator of GR tilde, it's the denominator of this whole mess. So it's a completely different denominator, and therefore it's a completely different stability problem, because I have a different D tilde. And what we find is when you have recycle, then things happen a lot faster. The system responds faster than no recycle. And why is that? Because if there's, that just sort of makes sense. If there's a perturbation in theta 0, so let's say the temperature of the input, then not only does that change the temperature of the output here, but that output gives me, with the heat transfer, gives me an immediate perturbation to theta 3 in addition to that of what was coming from theta 0. So it reinforces the effect of the perturbation. Now, why is that interesting? Well, if you go back, to the 1930s or the 1940s, energy was cheap. Even in the 1960s, if you look on the internet, and you look what gasoline cost, it was probably 30 cents a gallon. I don't know if anyone drives here. In New York, it's not as relevant as anywhere else. But gasoline is at least 10 times that price now. And so is energy. So in the old days, way before even Professor Ackervose's time, Professor Ackervose is 95 now, energy was cheap, so when they built plants, they didn't worry about these recovering the heat. They just turned on a furnace and heated this up directly. And the plants were easy to control because they were sluggish. They didn't respond right away to little perturbations. On the other hand, when energy got expensive after the oil embargo in 1973, all the prices of energy went up and they've never come down since. Now they say, well, why are we throwing this hot fluid away and then turning on a boiler? We can just contact the hot fluid with with stuff that needs to be heated up. Also, ditching the hot fluid in the river kills the fish. So you don't want to do that either. So it's not just energy, it's also the environment. But what that means is the plants today are highly heat integrated. They're always, you don't waste a hot stream if you have to heat up another stream. And everything is tried to integrate as much as possible to waste as little as possible. But what that means is that makes your job as the control engineer that much more important, because your system is much more sensitive and with these recycles. Are there any questions on that? Okay, so what else? There's a long discussion in the textbook after this about an example when you have stage processes. In unit operations, you look at stage processes, for example, distillation, extraction, etc., separation processes. And in stage processes, you have many different stages. And each stage in a stage process, the J stage, interacts with the stage above it and the stage below it. So for example, if I have distillation, I've got vapor coming up from the lower stage into the current stage and leaving to the one above it. And I've got liquid coming down from the stage above it to the stage of interest, and then going down to the stage below it. So when you actually model those systems, stage by stage, you do mass and energy balances. You do mass balances on the vapor, mass balances on the liquid. At one stage, you have an input coming in. At another stage, you have outputs. At the top, you've got at the top of the distillation column, you've got a condenser, where you can take out products and recycle whatever the liquid, whatever condenses. And at the bottom, you have a reboiler, where the liquid bottoms that come out, you heat them up, and what easily vaporizes goes back in the distillation column, and otherwise what comes out is your bottoms. Those are the products. In order to actually solve those systems, you have many more variables in your equations. You need all sorts of thermodynamic relations and various types of assumptions. And once you do that, you get a system where for each tray, you can write down these types of block diagrams. And then you've got a real mess of all these block diagrams that you have to then try to solve. So the point of that discussion is to show you that these techniques of coming up of block diagrams allow you to come up with overall G's that may have 100 little G's in them that you would never be able to get in any sort of reasonable manner if you tried to analyze the whole system at once. But by using block diagrams, you can come up with the block diagram and the overall G's for the outputs in terms of the inputs, where you try to eliminate all the intermediate steps. If you can linearize all those equations, if you can linearize them, you can write the output, say what's coming out of the reboiler and what's coming out of the condenser, the products, in terms of the feed, in terms of some overall G that has little g's, component g's, that come from all the things that are going on in the individual trays. Now, they don't give you that. They just sort of chit-chat about the problem. But that's the point of the problem. And I'm not going to reproduce all that. The idea is to impress on you that this notion of block diagrams, when you can linearize systems, allows you to take a system that has 1,000 intermediate variables, 2 outputs and 1 or 2 inputs, eliminate all the intermediates and write the outputs in terms of some big G times the little inputs, where that big G you can get from the little pieces of all the other things that are internal to the system. Okay, are there any questions on that? All right, what I may do, I'll figure it out next time, is I may just repeat an example I've done in the past where or I might not because I've done it on the blackboard already, where I looked at a system, say for example a CSTR, where you both change you have a perturbation of the volumetric flow rate as well as the inlet concentration. So I think I did in the past where you had, I probably won't repeat it, where you have two perturbations going on at the same time. As long as you linearize the system, you'll have a left-hand side that's the system, which would have the derivative of the variable of interest, the concentration, plus everything else that involves the concentration. And on the right-hand side, you would have the forcing functions. And one forcing function would be a v prime. You have something times the v prime, and then you have something times the CA in prime. So because you linearize the different forcing functions, just add. And if you remember, this is nice because in the equations themselves, I have a VCA. Remember, I have VCA in minus CA, VCA VT. And then I have plus R. One thing people didn't notice on the exam, except for like 2 people, is that when V prime changes, CA changes, so this product is nonlinear. People didn't seem to bother noticing that in part B of number 2, that when V changes, that changes CA, so this is nonlinear. So you need to linearize VCA. Before leaving, let's linearize VCA. V and CA are, if you remember, if I have f of x1, that's equal to f of x0 y0 plus the f dx x0 times x prime plus df dy x0 times y prime plus nonlinear. So in this case, x is v and y is ca. So this is v0 ca0, ca in cross ca0. That's this. And then the derivative of VCA with respect to V is just CA. So I've got CA0 times V prime. And the derivative of VCA with respect to CA is just V. So that would be how I linearize this term. And of course, VCA in is equal to V0 CA in 0 plus CA in 0 V prime plus V 0 CA in. So that's how I linearize both of these terms. And you notice the linearization is quite easy because when I take the partial derivative of this with respect to V, I just get CA, and the partial derivative of this with respect to CA, which is V. That was on the exam. I don't know if anyone got that, maybe one person, but that's also the key to linearization. Are there any questions? Okay, so what we do next is the next thing we're going to do. I may or may not do this in more detail. What I'll do is I'll write this problem out in great detail and just post it on the web, on Blackboard. So in the next class, so this is basically going to complete the material for the second exam. There are homeworks that you need to do, and I expect 100% of the people to be doing and in homeworks. You don't have to get them right, but you need to do the homeworks because it's the only way you learn the material. And we'll, once we get the homeworks back, we'll have an exam probably within the next 2 weeks. Probably the week after next would be when the exam would be. We're also, and we completed this, what we've completed now, the next thing we're going to do is we're going to start control. We spent half a semester looking at how to model and analyze systems. Now we're going to start control. And part of doing control is I'm going to teach you how to use Simulink. So at one class, on the next class or the class after, I'm going to bring in my computer and hopefully be able to show it on a beamer so we can actually go through Simulink and how to use it. Are there any questions? Okay, so there's still 4 people missing, but we're going to have back the exams. So